This is section 5.2, and this one's on logarithms, and I know that everyone's done some of this in Algebra 2. So this shouldn't be new to you. Some responses that I got from students in previous years is that they really were able to understand it this year, versus maybe in Algebra 2 they were a little rocky. So hopefully that's your experience. If you had a tough time with this in Algebra 2, that you'll, just seeing it a second time, a little bit older, you'll understand this. So why do we need logs? Logs let us undo exponential effects. So we just went through exponential functions in the last section, and this is like the inverse operation. How do you get, if you have 3 equals 2 to the x, how do you figure out what x is? How do you get x by itself if it's in the exponent? The only way to do that is to log both sides, and then you can bring the x out of the exponent and put it in front and get it by itself. So if you had to solve for this, you'd have to use logarithms. Much of the power of logarithms is their usefulness in solving exponential equations, which is that equation right there. Some examples of when you would use logs or how they're used. They're used in model populations, carbon dating artifacts. They help coroners determine the time of death. So think about something that's decaying exponentially or growing exponentially. You would use logs in solving for that. Computing investments, growth of bacteria, radioactive decay, population growth, sound decibel measures, earthquakes, the Richter scale, which we will do in this class, the brightness of stars, chemistry, pH balances, a measure of acidity and alkalinity, as well as many other applications. So these are very popular in the real world, how things grow and decay. Logs were invented independently by John Napier, a Scotsman, and by Just Berge, a Swiss person. And logarithms which they invented differed from each other and from the common and natural logs that are now in use. So Napier's logarithms were published in 1614 and Berge's were in 1620. So there were logs and then natural logs which have a base of e, where a log has a base of 10. It's a little bit different. This is a continuous growth decay, where this isn't. This is a base 10. So converting between logs and exponential functions. We'll start there. So if we had an equation written in logs and we wanted to change it to exponential, there's a way you do this. And this isn't math, this is basically just memorizing. So this would be written as b to the y equals x. If you wanted to change that into exponential. So going from log to exponential. And then if I wanted to go from exponential to log, this one here would be the log, and then that would be my base b of x equals y. So the only reason we would convert them is to solve for x, or solve for that variable that's in the exponent. So we're just going to practice converting from exponential to log form. So I want you just to pause and try to convert these on your own to see if you're able to do that. And again, this is really memorizing, so you should be able to do this for a test. And hopefully you're back, and I'm going to show you how to do these. So this would be log base 3 of 9 equals 2. The exponent is always what it's equal to. This one right here would be the log base 4 of 1/4 equals the exponent. This one right here would be the log base 3 of x equals the exponent. So this here is always the exponent. Now we're converting from log to exponential. This way always seems to go a little bit quicker for me. Go ahead and pause the video and see if you can do these three on your own. Okay, so this one right here, convert. Here it would be 2 to the 4th equals 16. That's kind of how I loop that around so I remember. This one right here, the log, the base would be 10 if it's not written. It's just a given that it would be 10. And if I loop that around, that'd be 10 to the negative fourth equals 0.0001. And then this one, 6 to the 0 equals 1. And if you look at all these, they're all true. True. This would be 10 to the 1 over 10 to the fourth, which is 1 over 1,000. 10 hundredths, oops, 4 zeros. Which would be tens, hundreds, thousands, 10 thousandths. And then this one right here is true also because any number to the 0 is 1. Our calculators work in two bases. They have a base 10 and a base E. Remember the number E is that continuous growth or decay, depending on if you're going down or up. On your calculator, you have a log button and a natural log button. The log button has a base 10 and the natural log button has a base E. So if you have log, it would have a base 10, or a natural log would be a base E. That's the only difference between the two. So if I was going to find the log of 17, go ahead and do that on your calculator right now. And same with the natural log of 5, and make sure that you're able to get both of these decimals to be sure you know how to use your calculator. So can you find these? And the key here is without a calculator. So I'd want to see work to get credit. If you just plug that in, there's a way you could do that. You wouldn't get any credit for that. So the first thing I would do, I don't know what the log is, so I'm going to change this to exponential. 2 to the x equals 16. And thinking about x would have to be 4 to make that true. So I solved this without a calculator, using the inverse of logs, which is exponents. This one here I'm going to convert to exponential because I don't know what log base 4 of 64 is. So this is going to be 4 to the x equals 64. And you can do this on your calculator, 4 times 2, 4 times 3, 4 times 4, to find what these are. And this x would be 3, would be the answer. And then this last one here, 2 to the x equals 1/4. And I'm thinking about this, and I'm thinking that this x has to be negative. So 1 over 2 to the negative, or let me just put it that way. So you'd have like 2 to the negative 1, which is 1/2, 2 to the negative 2, which is 1 over 2 squared, which is 1/4. So thinking this has to be negative because the answer is a fraction. So x is going to be equal to -2, as we saw in this one right here. Okay, graph this by hand. So the original one, y equals log base 4 of x, that's the same as 4 to the x equals y. And this way I'm able to actually plug some numbers in. So if x, I'm going to go with x because that's my input. If x was 0, this would, 4 to the 0 is 1. If x was 1, 4 to the 1 is 4. I could even go -1. So 4 to the -1 is 1 over 4 to the 1, or 1/4. And if I were to graph that, I'll do that one as blue. So I have 0, 1, 1, 4, -1, 1/4. And y could never be 0, right? So I'm going to have an asymptote here. Thinking this is exponential, just like we did in the last section. There's my first one. And then if I was going to graph the inverse, think of the inverse is you would exchange x and y. So if I'm going to exchange x and y, this is going to be 4 to the y equals x. And if I'm just exchanging x and y, if I were to plug in for y, that would be the same as the x. So remember, we're